such a interesting audience. It seems like I feel closer to home because you have like Latin Americans around and Portuguese people, so it's nice. So today I will talk about some work that I did together with Frank Reddick and Joa Carinci. The title is Higher Order Fluctuation Fields and Orthogonal Duality Polynomials. And this is more or less the outline of the program. It's kind of 3 parts. In the first 2 parts, I'm just going to introduce the basics. And then on one part I'm going to talk about one paper and the other one another paper, which have in common the same idea of really just combining duality over there, right? So let me introduce the processes. We will talk about interacting particle systems. So it's basically you have a bunch of particles on a lattice, let's say set D. Actually, it will be set D in all the cases. And these particles are hopping around according to some very simple rules. So the rules are so simple that these particle systems are considered as toy models. But however simple, they are interesting enough or rich enough that you can study with them interesting phenomena, right? Like what I'm trying to depict here on the right-hand side or left-hand side, it depends how you see it. It's just kind of condensation, right? You see that you have accumulation of particles, and so it's easy stuff, but good enough to learn something from them. And so this is sort of a artificial parametrization of these 3 processes, right? So trying to introduce easy notation, we combine or we introduce this by encoding the difference between the 3 processes that we care in terms of these 2 parameters, no? Actually, in terms of this parameter sigma and alpha. So sigma is the important one, is the one that determines the kind of dynamics that you have. And when sigma is equal to 0, it means basically that your particles are moving independently, right? Like they just move according to these Poisson clocks. You know, you're waiting for an exponentially distributed time, and then when your clock rings, you decide to move, and you don't care about what other particles are doing. And then when sigma is equal to -1, and for example, if you make this alpha equal to 1, is the very famous exclusion process in which you have this independent motion of particles, but with an additional rule, which is that you cannot have more than 1 particle per side. Then on this class of process, we're going to allow alpha to be a natural number, and that will represent really the maximum number of particles that you will allow per side, right? So the traditional one is 1, and then this is just kind of an alpha exclusion process, right? And then the opposite, when we have sigma is equal to 1, we have in a way the opposite dynamics, no? In the inclusion, you are preventing particles to come to a side, well, preventing more than 1 particle or more than alpha particles. And now in the case of the inclusion process, you are actually inviting particles to come, right? The more particles you have at the destination site, let's say here you're moving to I plus R, right? So the higher the chances to invade, or the stronger the attraction, no? Okay, so these are the processes, and then we will just talk about them. We would think of them as if you have already an infinite number of particles. Particles are in set D, as I already told you. And since we want to really exploit these systems, we're going to make some assumption on this transition probability, right? So this is the transition probability of just 1 particle moving around. And then we want the simplest of the situation, right? So we want to be in equilibrium, in actually to have detailed balance. And we're going to assume that this transition probability is symmetric. It has finite range, which means that particles can just move a finite amount in space, and it's irreducible, right? So that you can visit all the places, right? So that's really a lot to ask, perhaps, but we just want to say good stuff, right? So under these assumptions, we already know much about these systems, right? So we know that there is a family of reversible measures, what we really care about, I mean, what I care about is like that we have the self-duality property, and in particular, we have orthogonal self-duality. We know some very basic scaling limits also, no? Hydrodynamic limits and equilibrium fluctuations, because remember, we have reversible measures, so we are in equilibrium for the moment. Then just to give you an example of what we already know, so we know the existence of a family of reversible measures that are product measures and ergodic. And for example, for independent motion, we know that the marginals of these measures is Poisson marginals, when this parameter rho, in all the cases, is the density of particles, no? So we are parameterizing by that. And since there is no creation or annihilation of particles, everything, I mean, the number of particles is an invariant quantity. So we think of the density of the particles as not changing as the important one. Then for exclusion, for set alpha, we have negative binomials. And for the symmetric inclusion, we have, binomials for set. And for the inclusion, we have negative binomials as reversible measures. So that's nice. Then we have orthogonal self-duality is one of the other things as a consequence of having this nice, very nice setting. And then, I mean, this was the start of orthogonal duality. It was actually Ayala and Christian, the ones who introduced it. And then we just introduce some notation, right? So remember, this variable eta will represent the number of particles, and we will always think of it as a configuration with potentially an infinite number of particles. Then we introduce this notation, omega sub index k, which will represent the set of configurations such that they have exactly the number of particles in this configuration is exactly k, okay? And then this Greek letter psi, or this configuration psi of t, will always, I can say always and not, just a configuration of k particles for us, no? And then we just introduce additional notation. We call L of super index k the generator restricted to this omega k, no? So you just think of it as the generator of the dynamics with k particles. And actually, I didn't write it down here, but we also call omega f the union of these omega k's, no? So it's basically the space of configurations with finite number of particles, but you don't say how many they are, no? So we say that the process enjoys a self-duality or enjoys a self-duality property, in particular the orthogonal self-duality property, if you have a function from this product space to the reals, such that at the level of expectations, or at the level of semi-groups, if you wish, you have this equality, okay? Just why is this equality useful? You can just observe that on the left-hand side, you have the variable eta t, the one with an infinite number of particles, is the one that is evolving in time. And on the right is the variable psi t, no? The one with a finite number of particles. This really means that if you want to understand the system with an infinite number of particles, in a sense, it's enough to really look at the evolution of at the expectations with a finite number of particles to that process, no? And then this is at the level of semi-groups. Then we can also have a similar relation at the level of generators, right? Because basically, formally you just exponentiate. And then of course, lambda k acts on the psi variable. The generator k acts on the psi variable, and the generator lambda on the eta variable, right? Then on top of that, to make it even more simple, we ask these duality functions to be factorized polynomials, right? Where you have index on the sides of the places, on the sides of the lattice. So you really have products. This is the single side duality polynomials, and these are actually polynomials of degree k, right? And of course, the zero polynomial is just a constant, the constant one. And even more, we also want them to satisfy orthogonality relation, right? So this is really integrals with respect to the reversible measure, and then this is just the Kronecker delta. And I don't know why I have this notation, but to this I also would call it, I mean, the inverse of that. So that will be just A of psi, no? Because I don't know why I introduced that, but then, so we have a factorized form and orthogonality. So it's really nice. Let me just give you a couple of examples. So for the independent motion, we know that these orthogonal dualities, the single sides, are given in terms of this family of Challier polynomials, in which you see, no, you really have eta minus, I mean, n minus rho, the variable, so this is an n squared. And then you also have knowledge of the generating function, no? Then for the other two processes, for the set alpha, you have Krauschock polynomials, which is not really the polynomials, but a renormalization, the one that are duality, orthogonal dualities. And for SIP, you have Meissner polynomials. Now, just a small and simple application of duality so that you can see how it can be used, is that we can compute correlation functions of this type, no? So you take a duality function. Here you have the time evolution. You let the semi-group act just on this part, and then you take integrals with respect to new rho. So this is in principle a computation of an infinite number of particles, and then you can just reduce this in terms of the evolution of finite number of particles, right? So notice that you have here two different finite configurations, no? Can have order 3 or 10 particles each. And then this PT psi prime is really the transition probability of starting at time 0 in a configuration psi, and at time t arriving at psi prime. And then in particular, this small computation implies that we have positive covariances, no, for these duality functions, a positive correlated. And then just the proofs so that you can see. So it's just in the first step, we change this expectation by duality in terms of psi, right? Here is just the substitution of the expectation. So you sum over all the possible arrival sides, we call zeta. Then you put the integral inside, and then you just apply the orthogonality property, which reduces you just to this side that is equal to psi prime here, no? And yeah, it's as simple as that. But I hope that I can show you later that this will be very relevant for us, and it will be quite useful. Now, I already told you that for these three systems that we care, there is much that is known. In particular, we know scaling limits and we know hydrodynamic limits. I mean, perhaps already everybody knows what is a hydrodynamic limit, but let me just explain you very, very quickly. So we care the object to study in this case is the empirical measure, which is really the measure that is counting how many particles you have in the rescale lattice, right? Remember that the dynamics was in set D. Then you just rescale the lattice as 1 over n set D, and it's as the lattice is going to RD, right? When n goes to infinity. That's why you have here an x over n, right? So you are looking at this empirical measure seen as a measure value process in path space, and then hydrodynamic limit really concerns the convergence of this measure to a limiting measure pi. And for the three processes that we care about, that we are talking about in this talk, it is known that the limiting measure is absolutely continuous with respect to Lebesgue in RD, and that the density of this measure pi t is a weak solution of the heat equation, right? With suitable initial conditions that for the moment we actually don't care about in this talk. So, but then, and you can think of this as a law of large numbers, right? So you have, in principle, a random object which converges to a deterministic object, no? Then if you take your Bible, you can see that the way that you show this type of results is really using this Dynkin lemma, no? The Dynkin martingales. And without giving you much detail, okay, so you just integrate your measure phi with respect to test functions phi, suitable family of test functions. And just let me just call that integrated version this guy. So you have the Dynkin martingale for that guy. And if you really want to show that you have a weak solution of that, you would like to close this equation. No? Closing the equation means that you want to write the action of the generator. This is your infinite generator on your field, which is given by this integral, in terms of the field itself, but perhaps with some operator acting on this phi now, right? And since you have, as a hydrodynamic limit, a weak solution of the heat equation, you actually want this operator here to be the discrete Laplacian, for example, right? And thanks to duality, you can actually perform this replacement, and that's a nice use of duality. And you can also control the quadratic variation of this martingale to really argue that this martingale goes to 0, and you actually have a weak formulation of the heat equation there, right? I hope I'm not making a mess, but I see that there is a mess there. That's not important, just a use of duality. Then I told you hydrodynamic limits are some sort of large numbers. Then you can ask yourself if you have a similar result, but in the spirit of a CLT, no? A central limit type of result. And that's actually what you can do, right? So you take your integrated empirical measure, you subtract the mean, so you are centering, and then you multiply by this sort of rescaling, right? So fluctuations concern really the study of the convergence of this density fluctuation field, no? That's how we call this YT of I of n. Then again, in your Bible, in chapter 11, you see that you can characterize the limiting field YT as a solution of this martingale problem. And this martingale problem, I mean, you can do just by looking at the quadratic variation and looking at some sort of Lévy characterization, formally solves this SPDE, which is the SPDE associated to a generalized Ornstein-Uhlenbeck process. And I don't know if you remember, but in the hydrodynamic limit, there was no sigma involved, right? So really the hydrodynamic limit was the same for the three processes. This is thanks to duality. But now, at the level of fluctuations, in the equation, we really see the appearance now of sigma, right? So we have sigma here in the mobility, and also this constant sigma here, right? I mean, just as a curiosity. Then, in this context, we have a useful fact, a useful principle, which is called the Boltzmann-Gibbs principle. And before explaining it, let me just introduce some additional notation. So before we have the fluctuation field, which was some sort of integrated thing, remember that we have here eta of x minus rho, right? So we can really look at fields of a local function f. And these fields are done in this form, no? So you take your local function, when this is just the translation operator, the tau x, and then you subtract the mean of that local function with respect to the reversible measure, right? And this is sort of a generalized field. And then in particular, one particular case of this field is the density fluctuation field, no? So it's really the field of the local function f of eta equal to just eta at 0, but with an additional rescaling of n to the minus d over 2, right? And then the Boltzmann-Gibbs principle really tells you that in this regime, under this scaling, and because the number of particles is the unique conserved quantity, the fundamental field is the density fluctuation field. And with fundamental means that you can really make this replacement, no? That any field under this scale can be substituted by the field with this projection, not pi1 of f, p1 of f, sorry, where this p1 of f is really the projection of over eta 0 minus rho. Okay, so this is the formal statement of that projection. No, for all phi, then you take this. I mean, since the field is linear on the function, on the local function, you can actually separate it. No, so it's really that this replacement that you know is really the formal expression, the formal statement of that replacement, right? Is really this L2 p sense, 2 because of the square, you can replace one by the other, no? And then this becomes very useful, for example, also from chapter 11 of Landim, if you want to establish the fluctuation for zero range process. No, zero range process is a process that has intersection with our class of processes. And then over there, if you write the Dynkin martingale, in the integral part, you get a term like this, which you would like to write in terms of the density fluctuation field y, right? And the issue of, I mean, in the problem, the reason why we cannot just write it down is because of this G, no? G is really the rate that appears in the dynamics of the zero range. And then thanks to the Boltzmann-Gibbs principle, is actually the one that allows you to do this replacement, no? So basically, this quantity is this. We can write in terms of these fields that we introduce. And the Boltzmann-Gibbs principle tells us that we can make this substitution, but it turns out that this substitution is really just the density field with the discrete Laplacian of your test function and some extra factor, right? Which comes really from the projection. And then once you do this replacement, you close the equation, and then you can, I mean, the rest is, okay, is technicalities, important technicalities, but this is kind of a key step on the derivation of the zero range, of the fluctuations for the zero range process, right? So our main result really relates to trying to generalize these Boltzmann-Gibbs principles, and moreover, to make them quantifiable, not to get a quantitative version. And just before introducing that, let me just, I mean, before stating our main result of this part, let me just introduce some additional notation. So we define the spaces HK as those spaces spanned by duality functions, orthogonal duality functions, where the finite configuration is varying, no? So you just vary psi over all possible configurations with at most k particles. Okay, so the union of these HK spaces is dense in L2 of new rho. So formally, or at least let's say that you have an F that is nice enough such that this expansion makes sense. Okay, so whenever I said F is an L2 of new rho, I meant that F is nice enough that this makes sense. Then I define the projection, the K projection of, well, the projection of F in HK as follows, no? So you actually just cap the summation up to order K, no? So instead of all the J, so you just cap it, right? Which is really just by, I mean, it would be just a real projection, no? In the Hilbert sense. Then this is our generalized or our quantitative version of the Boltzmann-Gibbs principle, right? So we're making it quantitative because now we're giving precise rates. right? We are starting from k greater than 2. And now we are, if you look over here, in the original Boltzmann-Gibbs principle, you have the projection 1. And here you actually will have the projection k minus 1. Okay, so in a sense, we are extending this notion that the density field was the fundamental field in certain regime to higher regimes. And now, for example, the original Boltzmann-Gibbs principle was talking about H1, not here. So it was that the density fluctuation field was really the fundamental field of this space, and now we're making it for higher order polynomials, if you wish, no? So this will be like a higher order version of the Boltzmann-Gibbs principle, and it is sort of interesting. These rates are not sharp, and perhaps they can be improved, but that's the only thing that I could come up. That they really depend on the number of particles that you are talking about and on the dimension, no? Okay, so sort of interpretation is for this, then it will be that we can replace the field of any local function by the field of the projection, the k minus 1 projection, multiplied by a suitable rescaling, right? So before, we used to have the n to the d over 2, minus d over 2, sorry. But now we have even a little bit more of room to play with, right? And then potentially that could help us to make replacement when you are working with objects such that you have these different rescalings, right? So it's a little bit more, potentially more powerful, right? So that's about the interpretation. Let me just give you a few comments about the proof. First, this is just for equilibrium. So we managed to prove this in equilibrium. But we also could extend it, at least for the case of independent random walkers, to local equilibrium, no? When you really start from product measures, but where the density rho is like slowly varying, no? So you could have different densities around different points, no? So the proof is a little bit more involved. So I will just give you some comments on what can you do for just a special case, no? So you can consider this the field of the local function given by the duality function of two particles at the same place, right? This is actually a good example. It's a good idea to look at local functions because remember that we have this some sort of expansion, right? The duality function, sorry, in terms of duality functions, this 13. So all the ingredients will be there already, no? So if you look at this field, remember this first lemma or first application of duality that we obtained, right? So it is really here once you substitute really the expression of the fields, right? So you get these extra two factors by the summations, and then you have the transition function, the transition probability of two particles starting an x, and both of them ending at position y at time n squared t, right? Because you are accelerating time by n squared t. But this is transition function for independent random walkers, right? So the picture here is easier because we have independence, means that we can actually split this, no, as the product of just one particle going from x to y times the other particle going from x to y, no? Oh. Sorry. So as that product, no? But then we can really bound that by, since you can split it, you can take one phi of y, for example, with one of these transition functions to get this bound, no? Because you actually have, you can get the subnorm of that one, and yeah, just the sum of over y's of pxy is equal to 1. But of course, there is some issues because this part also depends on x and y. But what you can do is just because you have independent motion, you have this bound, no? Of Pn squared 0, 0, which is why you have it here, right? And then the other one, you just subtracted with the, I mean, bounded with, this is a typo, so this shouldn't be here, with the L1 norm of phi. Right, then you can substitute this bound already in the original quantity that you want to estimate, and basically you just have a constant that depends on phi, on the norms of phi, and on rho, because that's really the L2 norm of the duality. And with this kind of time integral of the transition function of an independent Walker that starts from 0 and ends up at 0. And then to get really these rates that we have here, remember that we're in the case k equal to 2, is just do an analysis by cases, no? So for example, if you have an estimate like this, which would come, for example, from a local central limit theorem, or there are estimates in convergence to equilibrium, for example, for the SEP alpha. So if you have an estimate like this, then you can basically separate by cases, no? If the dimension is 1, then you have this, and then you can imagine that you can really just compute this integral, no? And dimension 2, then it is like this, but you can just separate regions because you have integrability issues, right? By the 1 over r, sorry, that you have there. And then something a little bit more complicated, but still doable, I mean, it's not that much complicated, is that for dimension greater than 3, you really exploit the transients of the random walk to recover this bound, no? The bound of 1 over n squared, no? Okay, that was the first part. I don't know if there are questions up to this point. Otherwise, I can. Okay. So that was one part of the story. The other part of the story, let me just put a little bit of turbo. It is inspiring these two papers. And remember, we said that the first order fluctuation field is a solution of this Ornstein-Uhlenbeck process, an SPDE. And then you could have the question, I mean, there is some sort of motivation of how we can make sense of functionals like this, right? Because in principle, this Ornstein-Uhlenbeck process is a distribution value process, so it's a generalized function. And then we have issues with products of distributions, right? So what Milton Jara and Patricia Gonzalez did, they look at this object, no? So for the case of the set 1, and it was not on set D, but on the discrete torus, they define this sort of quadratic field in which now you have this product. Now, instead of just eta x minus rho, you have eta x times eta y minus rho. So it resembles some sort of quadratic field, and they study the convergence of this field. They show that this field converges to, I mean, that is to a field that is characterized in terms of this Martingale problem, in which now just look at the quadratic variation of this Martingale problem that really has some expression involving the field of the density fluctuation field, no? The first field that we found out. And then with this Martingale problem, they managed via a renormalization procedure, they managed to really make sense of this field. Now this kind of integration, you look at here, you are already renormalizing. And so they show that it converges to an actual field that makes sense, and they characterize this field. So I'm not going to talk about how they did it, but they just used the Martingale problem. And then there is this key observation, no, for us. So the first order field, as you might already notice, you can write it just in terms of duality functions, orthogonal dualities of just one particle, which in this, if you just plug these duality functions of two particles or the product of duality functions of one particle in these fields that we define in the Boltzmann Gibbs, morally they are the same, right? So that morally with the appropriate rescaling for us would imply that this quadratic field, you can really think of it as the product of these first order fields, which we will just define as the field of order 2, no? And then since already at the discrete level we have some sort of process, then we can imagine, we can dream that this relation survives the limit, where you have some sort of you have another product which is nice enough, right? And these HK spaces that we define, in a way, we can think of that as discrete chaos expansions. So that gives us the additional hint that to think of weak products in a way. So this, I'm not saying that this nice product is a weak product, but just that behaves like that. And then we just make the assumption, no, let's assume that this product is nice enough that follows the Leibniz rule of differentiation, no? So the product rule. So if you naively try to get the differential equation for this product of y1s with this product following the Leibniz rule, you reach this differential equation, right? That magically, well, not magically, but luckily corresponds to the Martingale problem that Patricia and Milton showed, right? So this really suggests that we could do the same at the level K, no? So that we can define fields of order K in which you just write down you just put the duality function of a configuration with K particles, right? So just naively that, weighted with some weights that really depend on these reversible measures in a way, right? These weights of the reversible measure. So that's really the second result. So we define these fields, and we hope to really just show the convergence of these fields. We didn't apply it to anything else. We didn't show this very nice application that they have. We just look at this. And then the conjecture will be just that this will be the SPD associated, no? It will be the SPD that you get by just applying naively again the Leibniz rule K times, no? Well, the Leibniz rules for K products. And this is really our result, right? So we say that this K order fluctuation field converges to a limiting K field, for which its Martingale problem is really a recursive Martingale problem, no? So it's a Martingale problem at level K that depends on K minus 1 and so forth. And when you have an initial condition, YT1, that is really the solution of this Ornstein-Uhlenbeck SPD, no? And then the way to show it, remember that we have this Martingale, these Dynkin martingales is by what I told you. No, you have the action of the generator on the field of order 2, just for simplicity here, right? Then you just use duality actually to change from here to here, right? So you have the generator acting on the eta variable, and then you just change it to the generator of two particles, because remember that here we have order 2 acting now on the Psi variable, right? And then that was the magic of these weights. these weights are such that this, you can look at this quantity at the one in the previous step as an inner product. And then this lambda is some sort of a measure such that the generator of two particles is self-adjoint with respect to this measure. Then that's why you just send the action of the generator to this function phi, right? And now we are in business because now we have already here, I mean, we close the equation, right? So this would really be the field of order 2 acting on this L2 of phi n, no? Of eta. So that's closing the drift. We can also exploit really the structure that we have because of the orthogonal polynomials. We have knowledge of the generating functions there, so we can really make computations very precise. So it will be really like magical if you wish, but it just works to also close the quadratic variation, right? Because remember, in the CRT regime, we don't want the quadratic variation to vanish. We want to write in terms of something else. And in particular, because of our martingale problem, we want to write the quadratic variation in terms of the field of order k-1, right? And that's precisely what we do. And if you wish, there is maybe even way to look at it as an application also of the Boltzmann-Gibbs principle, a little bit more involved, but the problem is that we only have, formally speaking, the Boltzmann-Gibbs principle for independent random walkers and set. And this is perhaps a good point to stop, 7:45. So just to give you a last remark. So the Boltzmann-Gibbs principle, I already told you, no, we did it also for non-equilibrium. What is missing there is for SIP, which is a bit hard because we don't have that estimate that we obtain from the local central limit theorem, or there is no other similar estimate, for example. And then there is a similar story also for at the level of this higher order, the second part, also at the level of hydrodynamics. And thank you. I don't know if there are questions or something.
Thank you very much, Mario. So let's see if there are any questions or comments from the audience. So one thing that I was wondering if you can also use orthogonal duality for asymmetric particle system to get information in this spirit regarding the higher order fluctuation field of the Boltzmann-Gibbs principle, at least in equilibrium, maybe.
In equilibrium, higher order, I think, yes. If you, I mean, it will just, I mean, I guess we will get really like close. I hope we will get closed forms in this part of the quadratic variation, which will be the harder part to deal with, I guess. But the rest, it seems that is plausible, right?
Mm-hmm.
For Boltzmann-Gibbs, I'm not really sure. I would really need to check with more care, because there are, I mean, there are like the part in which we split this transition functions of two particles to one. I mean, for the set, you can go around this because you have these correlations, right? You have like set has negative correlation, so probability of 2 is greater than split it. So I don't know if that still holds for asymmetric versions.
Okay.
That's the first thing, and I also don't know if we have like spectral gaps or things like that for asymmetric. Do we? I don't know. But at least for higher order fields, the picture is replicable.
Should be possible. Okay, thanks. Let's see if there are other questions or comments. I don't think it's the case. So thank you very much, Mario, for the talk.
Thank you.
Thank you. And we resume next Wednesday at the same time and same place. Bye-bye, everyone.
Bye.
Bye, Mario.
Bye.